Hi, in this video I'm going to show how to generate text from a recurrent neural network. What we're going to do is, given a phrase, we're going to predict the next character and then use that next character for appended to the original sequence for the next sequence for the next phrase, and then predict the next character and repeat that 400 times to generate a full paragraph. For computational efficiency, we are generating one character at a time, but this same experiment can be done with predicting the next word, and I think it will give better results. The material in this video was taken from the first part of chapter 8 from the Deep Learning book, Deep Learning with Python book from Francois Chollet, which is on the references. Okay, let's get started. To train the neural network, I use a book that was obtained from this PDF. So I downloaded the PDF and copied the text into a text file, which is in my local machine, this one. Okay, so let's run it. Then just by we read the text, the file into a text, which has almost a million of characters. And then to train the neural network, the input for the network is going to be the phrases, which we call here the sequences, and the output is going to be the next character, a single character. Okay, so we're going to use one-hot encoding. That means that instead of representing the character as an unsigned 8 integer, we're going to represent it as a set of booleans, in depending on how many characters, one boolean for each character. So each character is going to have an index and within a map, and then the corresponding index of the character is going to be true in the boolean array. The other ones are going to be false. Okay, so let's get started. So we need a set of sequences and a set of next characters. We are not building the tensor yet. We're just getting the sequences. The sequences are going to come from the raw text, the one that we obtained from this file. And we are doing it like a sliding window. So for example, the length of the sequences are going to be 60 characters. So we go from 0 to 59, and then the character 60 is going to be the next character, which we put in a separate array, and they have the same number of samples. Okay, so the number of sequences is almost a quarter a million samples. And now we want to get the number of unique characters that we have in this text, and that the number of unique characters is going to be the number of booleans that we're going to use in the one-hot encoding. Okay, so we're going to use set to get the unique characters, and then we're going to use a list in order to sort them. Okay, and also in order to get a map like a structure. Okay, so we have 88 unique characters, so we are going to need 88 booleans for one-hot encoding. And now the list has a neat method that called index, that given the key is going to give you the corresponding index. And that is going to be used to create a dictionary that goes from the character to the index, like shown here. And that we're going to use to create the tensors. So let's create the empty tensors first. The X is the tensor input tensor for the neural network, and Y is the output tensor. So the dimensions are going to be sentences, which is a sampling dimension, and which is the same in the input and output, and the max length, which is the length of the sequence, and 88 unique characters. This because the sequence are stored as characters, and the output is going to be the next character, so it's also 88, the second dimension. Okay, so we iterate through the sequences, and within the sequences through the characters, and that's going to be the first 2 dimensions, and the last dimension is going to be the dimension of the index, which we take from the dictionary that we just created. And so we're going to mark the corresponding index as 1. So that's the one-hot encoding here. And we're going to do the same for the output, but instead of using the sequence sentences array, we're going to use the next characters array. Okay, so we have the contiguous tensors for our neural network. Francois Chollet mentioned in the last chapter that neural network is a misnomer because deep learning neural networks are really contiguous tensor operations. they should be have another name, but they are still called neural networks for historical reasons. But they operate with contiguous data, so that's why we need to have tensors in here. So the input is going to be a tensor, the size of the length of the sequence and the length of the unique characters, and the output is going to be the classification, which that's why we're using softmax, of the 88 one-hot encoded characters. Okay, so the sampling dimension, the sentences dimension, is implicit, but you can see it in here in the summary of the network. We're going to use an LSTM, a recurrent layer, and for classification we use a fully connected layer, the dense layer. This is a very simple network, sequential. For the LSTMs is a type of recurrent neural network like GRU. GRU is less expensive. LSTM is more expensive but more effective, and it is good for problems that depend on the sequence. And here, this type of problem is about text, and it depends on the sequence, so it should perform better. But sometimes text do not depend on the sequence, and it might be more beneficial to use a one-dimensional convolution layer, which is less expensive as well. Okay, so in this case, we're using LSTM. And now let's train it. We're going to use RMS-prop, which is a very good optimization algorithm. And we're going to use the categorical cross entropy loss function for the training and a learning rate of 0.01. Okay. And now let's train the neural network. So we're going to have this to insert some entropy. The author mentions that if the next character coming out of the prediction is always going to be the one with the highest probability, then you're going to get some good looking generated text, but it's very predictable and boring. So we add some entropy to generate more interesting text. But if the entropy is too high, then we are going to start to generate garbage, and that's part of the experiment. In here we use low entropy 0.2 and high entropy. You're going to see the garbage in 1.2. okay. In general, he's making the training of the model for each epoch. We're doing the epoch manually, that's why we set epoch to 1 here. And after we train it with the input and output tensors, then we gonna generate the paragraph for each temperature. We just first pick up a phrase randomly from the original text. We pick up randomly the initial position, and then we pick up the phrase, which is 60 length. Okay. Now for each temperature, we're gonna generate a different paragraph, and we start with the phrase that we selected. Then after that, we're gonna predict the next character for 400 times, and so we're gonna generate 400 characters. That's the length of the paragraph generated. So first we need to get the tensor, and so we have an empty tensor with the size of the input of the neural network, and then we use the one-hot encoding with the dictionary, and we feed that into the network, and then we take the first we do this to eliminate the sampling dimension, so we get here the one-hot encoded predicted next character, and then we use the sample function. This sample function is to add the entropy, and then we use this map to get the actual character, and then we append it into the sequence, and then remove the first character, so we keep going for the next character until we generate a paragraph like this. Okay, so let's go just one iteration before getting into the result. Let's go to one iteration to see how it works. Okay, so let's pick up one sentence, and we have this sentence here. This is from the book. Okay, now let's create our input tensor. Let's use a temperature of 0.2, and we have an empty tensor with zeros, and then we use the dictionary basically we're gonna iterate through the text one character at a time, and then using the index we put one into a corresponding one. So we're converting this sequence into a tensor for the neural network. Okay, now we have the shape of the input, which is one sample. 60 characters and 88 for the Boolean one hot encoding. Okay, so now let's predict. Let's run it. Okay, so we have the output shape is one sample 88, so we don't want that a sampling dimension, so we get rid of the sampling dimension. And now we have what the author calls the predictable highest probability character. All of these are probabilities, so the index with the highest probability corresponds to the character that was predicted, and the sum of probabilities should be 1. That's a property that we should keep in mind. Yeah, this is 1. So now let's introduce the stochasticity. So we use a temperature of 0.2 and convert the character, the one hot encoding, into a float type, and then we apply the logarithm and divide by the temperature. That's where we introduce the stochasticity, and then to cancel out the logarithm, we apply the exponential, which goes in the opposite direction, but we already inserted the randomness. But now we lost the property of that the sum of the values are 1, so we are going to divide by sum to normalize it, and now we have the values addition is set to 1. And now we are going to use the random multinomial to basically get only the character, the index with the highest probability is set to 1 and the other one set to 0. So now we're just going to use argmax to get the index corresponding to this value. And that is index number 19. And from the map, we get the corresponding character, which is 9. Okay, so that's what basically this is doing. Is using this sample to introduce the stochasticity, and that is called after calling the prediction. So it's gonna be done 400 times to get the paragraph, and yeah, I'm basically training the model 60 times. Okay, so let's get to see the results. So we can see at the beginning that the noise is high. I'm not running this again because this takes a lot of time, maybe a couple of hours, depending if I was not able to connect my GPU to this Jupyter notebook, although I was able to do so very easily in MATLAB. But without GPU, the training is going to take a lot longer. Okay, so you can see that the first phrase that you see here comes from the book. And I think around here or something like that is the text that is generated by the neural network. So you can see, even though the training is low, you can see, yeah, at the beginning, you're gonna see words that might not exist, but many of the words do exist. It doesn't make much sense, but with temperature 1.2, with the highest randomness, you're gonna see a lot of garbage. Okay, so let's go forward to the epoch 59, which is the last one. And well, you still see a bunch of garbage with temperature 1.2. Let's see with 0.2. And yeah, the words look pretty good with 0.2. What about 0.5, the in between? The words still look good. Yeah, since we're predicting one word at a time, you don't expect that this makes a bunch of sense. If we were predicting one word at a time instead of one character at a time, it would be much better. Thank you for your attention.